Welcome to the Creative Paradigm lecture series. Today we will discuss the algorithm of the fractional knapsack problem using greedy strategy. So before going into the detail of the algorithm, let us first solve a numerical using fractional knapsack problem. In my last class lecture, that is under the same lecture series, I have discussed the fractional knapsack problem definition, and there also I have solved one numerical using fractional knapsack problem. Just as a recapitulation of the fractional knapsack problem definition, in gist, we can say that we are given n number of objects along with a knapsack. Knapsack means a bag. We have n number of objects I told. So assume that object I has a weight that is represented by a parameter wi, and the knapsack has a capacity, suppose it is m. So if a fraction, suppose the fraction is represented at xi, that is the fraction of the ith item, where the value of xi is in between 0 and 1. So it may be 0, it may be 1, or even in between 0 and 1. The objective is to obtain a filling of the knapsack that maximizes the total profit earned. So before that we must mention, if a fraction xi of the object I is placed into the knapsack, then definitely a profit is earned that is represented at pixi. And what I told, the objective is to obtain a filling of the knapsack that maximizes the total profit earned. And since the capacity is m, we require that total weight of the chosen objects to be at most m. So that is actually represented here. So here I told, if a fraction xi, where the range of xi is in between 0 and 1 of the item I is chosen, then a profit pixi is earned. Our objective is to maximize the profit subject to the total weight should not exceed the capacity of the knapsack. We have discussed three proposals, proposal 1, 2, and 3. The first proposal is based on the profit-based selection. So you have to select the item having highest profit. And the intuition behind this proposal is maybe fewer items, but more profit. Second proposal is based on weight. Definitely select the item with minimum weight. And the intuition is basically more items chosen means more profit. And the third proposal is a ratio based. Select the item with maximum profit weight ratio. So the intuition behind is a balance between the rates at which the profit increases and weight used, that is maximum profit per unit of weight. So we have discussed these three proposals based on which we have taken an example, and the example indicates we have three items. Capacity of the knapsack is indicated by 20. We have three items, definitely three parameters of the profits must be there, three parameters of the weights must be there. You have to have three different proposals. So I have shown all three proposals and calculated the total profit earned. Out of the three proposal, we have identified the last proposal, that is ratio based proposal. This approach is finally preferred because it earns the maximum profit. So based on these three uh, proposals, we have finally taken the last one to be accepted. So based on which we will go for writing the algorithm. So let me take the same example here. Suppose I have total number of items, suppose n equals to 3. I have the knapsack capacity m equals to 20. I have altogether three items. Definitely I have three weights, and the weights is W1, W2, W3. Weight of the first item suppose 18, weight of the second item suppose 15, and weight of the third item suppose 10. I am using the same data which I have already shown in my last slide. So associated profits are P1, P2, and P3. P1 indicates profit of the first item, that is 25. Profit used for the second item is 24, and third item's total profit is 15. So I have to now go for only solving the ratio based solution. So first of all, here my intuition is to select the item having maximum profit weight ratio. So before proceeding to that, let me calculate the ratio. That is, I have to calculate P1 by W1, P2 by W2, and P3 by W3. So based on the data given, I have P1 that is 25 divided by 18 here. P2 means 24 divided by 15 here, and P3 means 15 divided by 10 here. So based on this, I am getting the value of the first ratio, that is P1 by W1, which is actually represented as 25 by 18, and the ratio comes as 1.38. Second one comes as 1.6, and the third one comes as 1.5. So among these three, which one is the highest one? 1.6 is the highest one, which actually indicates item number 2. So I have to pick up second item first. Then I have to move on to the third item. Then if required, I will come back to the first item. So here also I have to calculate the solution vector, and solution vector is actually indicates the contribution of the item from the given set of items, and based on the contributing factor we will decide which item will be taken in how much proportion. So here the length of the solution vector will be equal to n. So length of the solution vector will be equal to n, and here n means 3. So basically solution vector is nothing but a one dimensional array. So its length is 3 here. So it is actually indicating the parameter that I told is represented at xi, and the range of the xi is basically 0 lesser equals to xi lesser equals to 1. So the value of this solution vector will be either 0 or 1 or a fraction. And in my last lecture, I told you that in this solution vector content, if there is a fraction, there will be an only one fractional value, and this fractional value indicates the item that was last selected or selected at last. So here I may indicate xi, so x1, that is the contribution of the first item, that is x2, here it is x3. So based on the observation, I have found that the second item is of having highest ratio. So I have to select the second item first. So we have selected the second item first. So what is the weight of the second item, which is W2, so 15. So what is the knapsack capacity M, which is 20. So yes, second item can be fully utilized because bag capacity is 20. So it can consume full second item into the bag. So it is an indication we are going to utilize full second item. So definitely the contributing factor of the second item is 1. So what is the, by formula, we are considering W2 into X2. So W2 means 15 and contribution is X2. So here it is 1. So you are actually utilizing the full weight. Fine. So now we have to calculate the remaining weight, remaining capacity actually, remaining capacity of the knapsack. So what is the remaining capacity? 20 minus 15, so 5 units. So now, which one is the next highest ratio among these two? So it is 1.5. So it is actually the third item. So now we have to pick up the third item. But unfortunately, I am not able to pick up the full weight of the third item because weight of the third item is 15. But unfortunately, the remaining capacity is 5. So we are not supposed to take the full weight of the third item. So I have to take the fraction part of the third item. So that is the deciding factor, how much I can utilize the third item. That will be indicated by the value of x3. So X3 is actually the remaining capacity of the knapsack, which was 5, divided by the weight of the currently selected item. So how much it is? 5. That is the remaining weight is 5. And how much, sorry, here the W3 equals to 10 here. I'm sorry. So here it is 5 by 10. So that is the contributing factor that will decide the amount of the second item, third item you are supposed to put into the bag. So what is there? So it is 0.5. So how much weight you can take from the third item? So it is nothing but W3 into X3. What is W3? W3 is 10. And what is X3? X3 is 0.5. So that indicates 5. So remaining capacity will be filled up from the third item, utilizing only 5 kilogram from the third item. So what is X3 here? X3 is 0.5. So what is the remaining capacity? Remaining capacity is now 0. Remaining capacity was 5, which is fulfilled by taking 5 kilogram of the third item. So now remaining capacity becomes 0. So there is no question to take the first item. So as there is no question arise to take the first item, so here x1 becomes 0. So here it is 0. Fine. So now we have to calculate the total profit. Total profit is P1x1 plus P2x2 plus P3x3 because it is as per the values, formula, it is I equals to 1 upon n, 1 to n Pixi. So by formula here n equals to 3. So you have P1x1 plus P2x2 plus P3x3. What is P1? P1 is 25. Doesn't matter because x1 is 0. P2 is 24 and X2 is 1. So you have utilized full second item. So full profit will be earned from there. You have third item profit is 15, but you have not utilized full third item. So X3 decides it. So 15 into 0.5. So how much it is? 24 plus 7.5. It is 31.5. So this is the total profit earned, which is the maximum profit. But there is a very interesting discussion now. So I am solving the problem. This is fine. I'm using pen and paper here. But ultimately, you have to visualize that computer is supposed to solve the problem. So once this is an assignment to the computer, you have to make an arrangement by which computer can understand which one is the first item. Actually, here the highest ratio holder is the second item, then third item, then first item. So to the computer, second item becomes the first one, third item becomes the second one, and first item becomes the third one. So if we make this type of arrangement here, then again we are supposed to get the same result. How can it come? So as per our data, our first item, our second item, our third item, it has this parameter that is W1 equals to 18, P1 equals to 25, W2 equals to 15, P2 equals to 24, W3 equals to 10, and P3 equals to 15. So after the ratio is computed, we have got the ratio as 1.38, 1.6, and 1.5. We have identified second item is of having highest ratio. So to the computer, the entire set of the second item comes as a first item values. So it is the first item to the computer. Third item, as per our data, becomes the second item to the computer because computer accepts the item arrangement in such a way it will treat the first item having highest ratio. So though it was second item by chronological order as per the problem statement, but here it will be treated as a first item, and third item becomes the second item, and our first item as per the data becomes the third item to the computer. But if you can consider this type of arrangement, you will get the same result as you have obtained, that is 31.5, because computer will treat it as the first item. Then as per the computer, it will be like first, second, and third, that is the solution vector. It is first treating this second item as a first item, then it will consider its weight. Yes, 15 kilogram weight, 20 is the capacity. So full utilization of the 15 kilograms. So definitely solution vector value will be 1. Remaining capacity becomes 20 minus 15, that is 5. Then second item, it was actually the third item. It becomes the second item to the computer. What is its weight? Its weight is 10 kilogram, but 10 kilogram cannot be accommodated full into the knapsack because remaining capacity is only 5. Then you have to calculate the fractional contribution. Fractional contribution by formula, it is remaining weight by the weight of the current item. It is 5 by 10, that is 0.5. So it will be 0.5. Remaining capacity becomes 0. So no question arise for the third item, which was actually the first item, treated as a third item to the computer. So no question to take the third item to the computer. So it becomes 0. Then the total profit becomes P1x1. What is P1 here? Here P1 means second item's profit, which is 24 into 1 plus. P2 means actually as per the data it is P3, but to the computer it is P2. That is the second item profit. So it is 15 into 0.5. So there is no question to take the third item to the computer, which was actually the first item. So though it is 25 into 0, so what is 25 in 24 into 1? That is 24, 15 into 0.5, 7.5 plus it is 0. So again 31.5 comes as a result. So this type of arrangement needs to be kept in mind once you are going to implement this algorithm in your lab. So now we are now moving to the algorithm. This is very simple, but before going to that, you must know one very interesting thing. Assume that some of the data set is given as you have altogether, suppose three data, that is three items. What of may be the value of the weights, what may be the value of the profits, what may be the value of the capacity of the knapsack. Assume that the capacity of the knapsack is only 20. And the ratio of the first item is first item ratio, suppose some value, second item ratio, suppose some value, third item ratio, suppose some value. Assume that the third item ratio is the highest. So assume that the weight of the third item is 25. Weight of the third item is 25. But fortunately, the ratio of the third item, that is profit weight ratio of the third item, is the highest one. So you have to pick up the third item first. But what is its weight assumed? Weight assumed is only 25. But what is the capacity of the knapsack? Capacity of the knapsack is only 20. So at the very beginning, you are not supposed to put the full third item into the bag. You have to take a fraction of the third item. And what is the fraction of the third item? That is the 20 divided by 25. So this is the value of the x3. So once it is happening, there is no question to take the first item and the second item, because unfortunately you are not allowed to put the third item full into the knapsack at the very beginning, where the ratio of the profit weight of the third item was highest. So as the third item could not be accommodated full into the knapsack at the very beginning, so question does not arise to pick up the first item or the second item, because here I told you repeatedly, the fraction once arise, it is indicating that the fraction of that particular item will be treated as the last item. After that, there is no question to pick up any item remaining. So here this scenario happens at the very beginning. So if this situation happens, then there is no question to pick up the remaining item, because the very first selected item is unable to take the full contribution into the knapsack. So this is one interesting thing you have to keep it in mind. Various combination may arise here, but you have to design the algorithm in such a way so that it can cover all sort of possible combinations. So now let us move on to the algorithm. So here the knapsack is the greedy knapsack is the name of the algorithm, and there are two parameters. M is the capacity of the knapsack and N is the number of items. So here P1 is to N is the profit array and W1 is to N is the weight array. We have already mentioned in my last slide that there are three weights, there are three profits. So how they can be stored? You have to consider one array, you have to consider another array. Here it is a profit array, here it is an weight array. So all this weight should be stored in an array. Another all set of profits will be stored in a one-dimensional array. So that is displayed in the next slide here. So P1 is to N, that is N number of profits are stored into P array, that is a profit array, and N number of weights are also accommodated into weight array named as W. Contains profit and weights respectively of N number of items, ordered such that Pi by Wi greater equals to Pi plus 1 by Wi plus 1. So this is an indication. The algorithm assumes once it is going to be executed, before that there should be a pre-processing. That means you have to arrange the data in such a way so that the first item to the computer will be treated as a first item once its profit weight ratio is the highest one. So you have to arrange the item in such a way so that the first item means the first item having maximum profit weight ratio. So that is an indication that contains profit and weights respectively of n items ordered. They should be ordered in such a way so that the ith item profit weight ratio should be greater than I plus 1th item profit weight ratio. So as per our example in our last slide, I have quoted that the ratio of the second item is the highest, third item is the second next, and first item is the last one. So as per our algorithm, this will be the first item, this will be the second item, and this will be the third item. Okay. So you have to make this kind of arrangement. So M is the knapsack capacity and X, 1 is to N is the solution vector. You know X1, X2, X3, I have computed there. And be careful, you please keep this in mind. The solution I have made, the solution which is assumed as the computer is solving the problem. Okay, it is not that you are manually solving the problem. It is the computer who is responsible to solve the problem. So to the computer, first item means the first item having highest ratio, second item means the second item having the next highest one. In this way computer will treat this. Okay. And one more interesting thing before moving to this one thing you just notice here, suppose this is the final solution vector obtained so far. If somebody initialize this solution vector as all 0, x1, x2, x3, or you may consider this one also an example, all are initialized by 0. Once some non-zero entity comes, this 0 will be replaced by this non-zero. And if something non-zero is not coming, so this 0 remains unchanged. So this is one of the tricks, that solution vector should be initialized by 0. That indicates no item is being utilized. If some of the non-zero replaces this 0, this means this is the contributing factor of that particular item. If some of the values were initially 0 and remain 0, even if the method completes, that indicates those items have not been utilized or rejected. So here, just see this one. We are initializing the solution vector as all 0. So suppose the solution vector is of having length 3, x1, x2, x3 are all 0. Later on, it may be replaced by 1, it may be replaced by 0.5, it may be 0. That means it was 0, it is 0, it will be 0. So there is no change. That means third item is not utilized. And again, I'm repeating, third item means that item having least profit weight ratio. Second item is that item having second highest profit weight ratio. And the first item means that item having maximum profit weight ratio, so that it can follow this one, P1 by W1 greater equals to P2 by W2 greater equals to P3 by W3, this one. Okay. So let us initialize the solution vector by all 0. Now we are keeping the backup of the knapsack into a variable, suppose W. So why this backup is required? This backup is required only because if somebody asks you to verify, once you have finished filling up the knapsack and your profit is already earned, somebody may claim that please verify whether whether the total weight of the knapsack exceeds the maximum capacity of it. So in that case, you need to hire M. But if you utilize M and M is getting modified by calculating the remaining capacity, so in that case, you are not supposed to get back the original value of M. So let us keep the backup of M into U. You use the value of U and keep M unchanged. So original value of M may be asked to verify this one. So I have written this here. So somebody may ask, your method is finished, you have calculated the profit. So let us verify total weight into your knapsack, whether it exceeds the maximum capacity. So in that case, you have to hide the value of M. But if unfortunately it is changed, you don't have to take back the value. So better to keep the backup of M into U and use the value of U for this purpose. Okay. So altogether, you have n number of items. So you may not know whether all items can be utilized, whether some of the item may be utilized, whether only one may be utilized, whether maybe two can be utilized, whether all can be utilized, we do not know. So we have to cover the full range, and the full range of item means altogether n number of items. So now, if the weight of the ith item crosses the capacity of the knapsack, that means the item which you have selected now, its weight is more than the capacity of the knapsack. Then you are not supposed to use the full of this item. So in that case, you have to calculate the fraction of this item. Otherwise, if the capacity of the knapsack is greater or even equal to the weight of the currently selected item, then that item can be fully utilized. But if the weight of the ith item is greater than the remaining capacity or even the initially the full capacity of the knapsack, in that case, you are not supposed to utilize the full item of that particular one. So that is an indication. If weight of the ith item crosses the capacity of the knapsack, and capacity indicates either the first selected item is of having more weight than the capacity, or after certain stages, the currently selected item having the more weight as compared to the remaining capacity. Capacity means this one, either the remaining capacity or the full capacity, whatever may be. So if the weight of the ith item crosses the capacity of the knapsack, then apply brake. That means you are not supposed to utilize the full weight of that ith item. If it is not, then you are supposed to utilize the full weight of that item, and in that case, solution vector value of that particular item is 1. That means you are utilizing the full weight of that item. And once it is done, you have to calculate the remaining capacity, because in our numerical solving, I also showed here. So once you are utilizing the item full, once it is done, then calculate the remaining capacity. So this is done here. Calculate the remaining capacity. Then once you calculate the remaining capacity, then move on to the next item for further verification. If the next item can be fully utilized, it is good. If the next item cannot be fully utilized, then you have to apply brake. So one thing you notice, once a particular item cannot be fully utilized, then you have to come to calculate the contribution of that item. That means once that item cannot be fully utilized into your knapsack, then you are supposed to take a fraction of this item. And once you are going to calculate the fraction of this item will be treated as the last item so far. Because I repeatedly told, once the situation comes that you are going to utilize the fraction of a particular item, this selection is the last selection. So that is why it is indicated once the weight of the ith item crosses the capacity of the knapsack, then it is an indication this is the last item. There is no question to go for the selection of the remaining items. No. So you will come to the out of the loop and calculate the fraction. And the fraction means remaining capacity divided by the weight of that item. And that value is the contributing factor stored into x of I. Then what is the necessity of this if I lesser equals to n? The necessity of this is, for an example, your second item contributes 50%. So in that case, the value of I becomes 2. I indicates 1 means first item, I2 means second item, which is within the total number of items. It may happen that is you have altogether 3 items. First item full utilization, second item full utilization, third item is of having fraction. So in that case also the value of I equals to 3 and n equals to 3. So at most you can go up to the last item. So in that case last item may be fraction. It may be second item out of 3. The second item may be of the fraction, or even if the very first item can be the fractional, because first selected item is maybe of having more weightage as compared to the capacity of the knapsack. So if it is within the total number of items of the uh, uh, given one, so in that case you have to calculate the fraction of that particular item, in that case where the weight of that item crosses the capacity of the knapsack. So you have to calculate the fraction of the last chosen item. I am repeatedly telling last chosen item. And that is why I told you that the fraction comes means you are about to close the method, because you have identified this is the last item after which no items can participate. So here in this algorithm, profit calculation is bypassed. You may introduce at the time of implementation, that is the profit calculation. So here also you know the formula PIXI, summation I equals to 1 to n. So here summation means you have to incorporate a loop structure. loop I for I equals to 1 up to n. You have to update the profit as profit equals to profit plus pi into xi. And the variable profit should be initialized by 0.0 because it is a float value. Okay, so this is about the ratio based algorithm of the fractional knapsack. The very last one I will conclude by considering the analysis. So disregarding the time to initially sort the objects, if our assumption is this pre-processing is a mandatory, that means you have to order the items in such a way so that the first item becomes the first item having the highest ratio. So this arrangement is by default to be maintained. So that is why it is written disregarding the time to initially sort the objects. Each of the three strategies mentioned in the last slides requires only order of n times because at most all items can be selected. Okay, if there are three items, the weight of the three items, summation of the weight of the three items may be less than or even equal to the maximum capacity of the knapsack. In that case, in the worst case, all items can be chosen. All items means all n number of items. So in that case, the time requirement will be big O of n. Out of three, maybe two items can be given. So again, it is big O of n. N minus one number of items have been taken. So it is linear. So big O of n is again coming back. So what are the applications? Oh, one more thing. If somebody may consider that I need to apply the sorting followed by the knapsack, then the optimum sorting algorithm takes order of n log n as a time complexity plus order of n here. So order of n log n will be the final complexity then. So what is the application? In logistics, it can be used to determine the most efficient way to load a truck with a given set of items. It is an logistic based application. Even if you talk about the finance, it can be used to choose which investments to make in order to maximize return while staying within a budget. This is just some very real life applications of the knapsack problem, fractional knapsack problem. Okay, so at the very end, again I repeat, we are solving the problem here means we are writing the algorithm. Algorithm writing means actually it reflects that computer is designing this algorithm. So be careful about it. Okay, so this is what about the discussion of the algorithm, which is ratio based algorithm of the fractional knapsack problem along with the complexity analysis. Thank you.